DMG. You get a red color complex, NIDMG twice. It is also a chelated complex. Okay. And even EDTA, one of the important applications of EDTA. When some people consume poison, like poisoning, accidentally or intentionally, the poisonous, the metal ions present in the poison, so doctors administer EDTA into the stomach. So EDTA forms coordinate covalent bonds with the poisonous metal ions and form a stable complex. That complex can be just emitted out by or vomited by using certain emetics. Emetics means vomiting agents. There will be certain vomiting agents after doing this. So the entire stable complex will come out. That's how they remove the poison from the stomach. And also we discussed EDTA is used to measure the degree of hardness of water. The degree of hardness of water is measured by EDTA. CO EDTA minus exhibit what kind of isomerism? This also discussed. CO3 plus EDTA 4 minus gives CO EDTA single minus. So that one cobalt 3 plus ion form how many coordinate covalent bonds? 6 coordinate covalent bonds, because cobalt 3 plus, chromium 3 plus always exhibit a coordination number of 6. So 6 coordinate covalent bonds are formed by a single ligand, that is EDTA. So CO EDTA minus exhibit optical isomerism. That is the chiral molecule. It can't have a superimposable mirror image. It has a non-superimposable mirror image. So the next question is regarding beryllium chloride. BeCl in vapor state is linear with sp hybridization, and the bond vectors cancel with each other. Mu is equal to 0. A linear molecule, non-polar in nature. Now, same B, this is in vapor state. Same BeCl2 in the solid state, each chlorine forms a coordinate covalent bond with other beryllium atom, because beryllium has vacant orbitals, and this chlorine forms a day-2 bond here. Like this it continues. So it has a polymeric structure. BeCl2 has polymeric structure in solid state. With chlorine bridges. The chlorine is the bridging. The structure of beryllium chloride in solid state, chain structure, and in vapor phase, maximum 2 units can combine in vapor phase. So vapor phase, this can have maximum dimeric structure, not polymeric. Yes. This is a dimer. Example, the diagonal relation. Aluminum chloride is also a dimer. AlCl3 in vapor phase is a dimer. Actually, this is a more familiar example for dimer. Al and B are diagonally related. When BeCl2 is dimer, AlCl3 in vapor state, it is a dimer. Dimer means two units are joined with each other. In carboxylic acids, you have studied acetic acid is also a dimer in vapor state or in non-polar solvents. So this H plus O minus form intermolecular hydrogen bond. So this is acetic acid dimer. This dimer exists in vapor state or in non-polar solvents like benzene. Now the next one, current structure of 2,4-dimethyl JEC4E. That is directly you can do that. Next one, right option for the statement of Tyndall effect. Actually, Tyndall effect, Brownian motion, we were not only studying chemistry, actually in chemistry, it is now out of syllabus, surface chemistry. So the next question is out of syllabus, but in biology we discussed this. Scattering of light by colloidal particles is known as Tyndall effect. What is Tyndall effect? Scattering of light by colloidal particles is called Tyndall effect. So because of Tyndall effect, the sky appears blue in color because the atmospheric dust particles scatter the light. Thus the sky appears blue. Seawater also appears blue. So for many years people believed that the reflection of clouds, the sky in seawater, reflection of blue sky in the seawater is responsible for the blue color of seawater. That was a misbelief for many years. But when our Indian physicist, Sir C.V. Raman, while traveling to the US, he is a professor in one of the prestigious US universities in physics. While he was traveling in a ship, he observed the seawater. It appears blue. And he believed that it is not the reflection of the sky, the blue color is visible. It is due to scattering of light. So immediately after reaching US, he performed light scattering experiments on different solvents by taking liquid water, by taking benzene, by taking alcohol. He conducted light scattering experiments on different liquids, pure liquids, and he discovered the Raman effect. So the Raman effect is so famous, so precise, and immediately the Nobel Committee announced Nobel Prize for Physics. So in the Swedish Academy of Sciences, when the prize was announced and distributed, is given to C.V. Raman, many distinguished physics professors attended the meeting. So they also asked to show the scattering of light on different liquids. So immediately Raman brought this equipment. He showed how the scattering applied in different liquids. So he showed in water, in alcohol, in ether, in benzene, carbon tetrachloride, many solvents. He showed how the light scatters. So immediately that experiment is over. The prize was given. Immediately they offered some alcohol. Because in high society, after an event, they will distribute alcohol. Because the Raman was an orthodox Hindu Brahmin from Tamil Nadu. They are very rigid people, very orthodox. So he rejected. Then they joke, all the distinguished gathering joke. My dear Raman, you have delighted us. You have delighted us by showing Raman effect on alcohol, scattering of light on alcohol. We want to see the effect of alcohol on Raman, the reverse. Men also simply laughed but did not oblige the request. So once we are very strict in our rules, nobody can impose. Many people say, no, it is social drinking. So in party only I take drink. That is obligation, they oblige. Some people say, no. No means no. So that is about scattering of light is shown by colloidal particles. Here only starch is colloid. Out of the 4 options given, starch is a colloid, your blood is a colloid, milk is colloid, clouds are colloids. So colloids, somebody asked, I think who asked, lyophilic colloids, lyophobic colloids, he asked. So philic, phobic, 2 Greek words. Philia means liking, phobia means hating. So in colloidal, there are 2 phases, like in the solution. One is solute, the other is solvent. Solute plus solvent is equal to solution. It is homogeneous. But in colloids, we use a different terminology. The solute is called dispersed phase. We call it DP. The solvent we call dispersion medium, DM. If DP and DM are liking with each other, then it is called a lyophilic colloid. If DP and DM are hating with each other, lyophobic colloid. Lyophilic colloids can be easily prepared because they are liking with each other. If you add dispersion phase to dispersion medium, colloid is formed, like starch. But if you want to prepare gold colloid, very difficult. You have to take 2 gold rods. They are connected to high discharge potential. They are immersed in water containing alkali. Now you have to create an electric arc, but already gold rods are immersed in water. So high temperature arc is produced inside the water. Due to the arc temperatures, some gold atoms evaporate. But they are already in liquid. They condense and acquire the size of colloidal particles. So that much difficult to make a lyophobic colloid. Gold sol is a lyophobic colloid. Sol means any colloid can be called as sol, S-O-L. We have studied sol gel theory. I think locomotion in amoeba, you have discussed, you studied sol gel theory, pseudopodia comes. I remember I studied biology in 1980. I think sol gel theory is in the locomotion of amoeba. It is pseudopodia. You check your biology. Okay, anyhow, the next one is out of polymers. Here the Teflon is a polymer, but Teflon They can ask you as a question in P block flooring applications. Teflon is polytetrafluoroethylene. This is tetrafluoroethylene. N molecules. So what are the favorable conditions for polymerization? High temperature, high pressure, catalyst. Usually the catalyst is Ziegler-Natta catalyst. Dr. Tony, what is Ziegler-Natta catalyst? Dr. Ricky Ponti, Ziegler-Natta catalyst. Dr. Rudolph. Yes, anyone. We discuss in D block. Titanium tetrachloride plus trialkyl aluminum. Titanium tetrachloride plus trialkyl, trimethyl aluminum is called Ziegler-Natta catalyst. So polymerization of many hydrocarbons require a catalyst called Ziegler-Natta catalyst. So for which 1963 Nobel Prize they received. Now the addition polymerization involves this pi bond shift like this. When pi bond shifts, a bond is connecting these two. When this pi bond, another bond, like that you will get an addition polymerization. You will get a linear chain in which C2F4 is a monomer and it linked with many units, N units. It is called polytetrafluoroethylene. Polytetrafluoroethylene, PTFE, which is popularly called as Teflon. Many applications of Teflon. Nowadays they are using Teflon coated utensils for cooking purpose, Teflon coated pans, tawas. So people claim that you can use less oil and make food in that. But the problem was this Teflon in the process of preparing food materials in hot conditions, they are releasing some free radicals which are carcinogenic, cancer creating. Thus, nowadays scientists are advising us to not to use Teflon coated vessels, not to use aluminum alloyed vessels. Aluminum alloyed vessels cause brain damage, causing dementia, Alzheimer's and all. And Teflon coated vessels cause cancer. One of the reasons for cancer is free radicals coming from this one, high electric potential, high electric discharge lines, using of too much plastic, So microplastics are entering into our body. That are also one of the triggering factors for cancer. So there are many triggering factors, pollution factors, high potential fields when we are working, too much usage of radiation devices. So these are all triggering factors for cancer. Now the deficiency of RBC, which is produced in bone marrow. As a biology student, you know that. Bone marrow produces erythrocytes, red blood cells. So these erythrocytes, if they are less, that causes bloodlessness. It is called anemia. Actually, it is called pernicious anemia. So pernicious anemia can be easily treated nowadays by using vitamin B12 tablets or capsules. If it is too low, doctors may give intramuscular injection, vitamin B12 injection. So vitamin B12 deficiency causes pernicious anemia. So the correct sequence of bond enthalpy of CX bond is where is our engineer? Actually, yesterday only this is gone. Battery should be changed. Any substitute engineer? Change the batteries. No batteries also. We will manage. So actually the carbon halogen bonds, CF bond, CCl bond, CBr bond, CI bond. Carbon size is same, but other halogen, bonded halogen, their sizes are increasing. Bond length increases, bond energy decreases. That's why the decreasing order of bond energy, CF greater than, CCl greater than, CBr greater than, CI. This is the decreasing order of bond energy. Here one more related point we want to discuss. That is, the bottles contain alkyl iodides become dark or black. This is assertion. What is assertion? The bottles containing alkyl iodides become dark or black. Now, the reason is in this question. The carbon iodine bonds are weak, so that's why alkyl iodides decompose, liberating iodine. The iodine sublimes on the walls of the glass vessel. Why they become dark or black? Because alkyl iodides easily decompose. Why they decompose? Due to less bond energy of or weak bonds of carbon iodine bonds. When they dissociate, the I atoms are liberated. They combine to form I2 molecules. I2 in vapor state it is violet, but in the solid state it is a greyish black solid. So the liberated iodine vapors, as the laboratory bottles are closed, they can't escape this sublime. Iodine has the property of sublimation. So whatever the vapors liberated, they again deposit on the inner walls of the glass, and the entire bottle become dark or black. This is a very important point in our syllabus. Next is Professor Firat, 78, empirical formula. When the percentage composition is given to find out empirical formula, you all know percentage by atomic weight, you will get certain numbers. 78 by 12, 6.66, and the remaining is 22% is hydrogen, 22 by 1, 22. When you get these two numbers, you have to divide these numbers with the smallest numbers. 6.66 by 6.66, that gives 1. 22 by 6.66 gives 3. So that becomes CH3, that is empirical formula. Among the following alkaline earth metals, which is covalent and soluble in organic solvents. Actually, this is in terms of alkaline earth metals, it is out of syllabus. But in terms of chemical bond, it is in the syllabus. Because beryllium chloride is covalent, because Be2 plus ion has high polarizing power. That's why beryllium chloride is covalent. When it is covalent, it is soluble in non-polar solvents. So the answer is beryllium chloride, and its brother, diagonal brother, aluminum chloride is also covalent. So both BeCl2 and AlCl3, both are covalent due to the high polarizing powers of Be2 plus and Al3 plus. Both BeCl2 and AlCl3 are covalent due to the high polarizing power of Be2 plus and Al3 plus. It is sp2 trigonal planar. Mu is equal to 0. So when it is a Lewis acid. Because it has a vacant orbital. But instead of accepting a lone pair from the outside molecular ion, its own electron pair of the fluorine is back donated to boron. So in BF3, back bonding is possible. In BF3, back bonding is possible. So a double bond character for one of the BF bond. So what is the bond order of BF bond in BF3? So one bond is fixed between B and F. The double bond which is formed will come from that fluorine or this fluorine or this fluorine. 3 fluorines can contribute like that. H is given negative. It is an exothermic reaction. A gives B. Now A has this much energy and B has this much energy. This is energy of A, energy of B. The difference in between reactant energy and product energy. This is delta H. This is given as minus 4.2 kilojoule per mole. So whenever delta H is given negative, reactant is at higher energy, product is in lower energy. That you should know. And the reactant A must gain some extra energy to cross the energy barrier. That is called activation energy. That is also given, but which is not required. This is 9.6 kilojoule per mole. So that is a very easy question. The compound which shows metamerism. So metamerism is shown by ethers ROR and ROR dash. The alkyl groups must be different. Functional group is same. Ethers are one type. Ketones. Ketones also show metamerism. R C double bond O R and R C double bond O R dash. So R must be different. The third compound, secondary amines, or directly we can write secondary is nothing but 2 degree. 2 degree amines. So RNH R and RNH R dash. Secondary amines, ketones, ethers, esters. Esters also exhibit metamerism. RCOO R and RCOO R dash. Now the last example, N hydrides. N hydrides. RCO OCOR and RCO OCO R dash. So provided they should have same molecular formula. Should have the same molecular formula. That is a condition for any kind of isomerism. Next question. Zirconium and hafnium have same atomic radii due to lanthanoid contraction. Which one?
Question number 8.
Question number 84. Which option? C3H8O. C3H8O is not the general formula of ketone. It is an alcohol. CnH2nO is ketone. Ketones are having CnH2nO. If N is equal to 3, you will get C3H6O. This is ketone general form. But the second option is C3H8O. So that is CnH2n plus 2. So this gives alcohol and ether. Ether is there, yes. Then what you get? C3H8O. You can write CH3O, CH2, CH. It won't give, because even if you change that, this side, suppose this is, you also write like this. Both are same. So some carbon alkyl group should be bigger. So though ether can exhibit, this compound cannot exhibit. From butanol onwards it will exhibit. Suppose if it is C4, C4H10O, this will exhibit. C2H5O, C2H5. The other is CH3O, C3H7. You can have two diethyl ether, methyl N-propyl ether. Like that you can. For question number 85, it is lanthanoid contraction. But here students should recall what are the three properties affected by lanthanoid contraction. Similar size of zirconium and hafnium, or similar size of atomic sizes of 4D and 5D series. 5D series elements have more ionization energy than 4D. When compared to 3D and 4D, 4D and 5D elements resemble much more closely. These are the three reasons or three properties affected by lanthanoid contraction. Now we are going for the question number 86. So there are two lists are given. One is FeCN6 3-, means here Fe is in +3 state. In +3 state, it has 3D5, 4S0. Now Cn minus is a strong ligand. When strong ligands, 6 strong ligands approach the ferric ion, they force the pairing of electrons. So this electron is paired up with this electron is paired up with this. So due to pairing of electrons, Fe3 plus configuration changes into one pair here, one pair here, one single electron. So 5 become 2 pairs plus 1. Now this D2, S and P3. D2 sp3 hybridization. Now each Cn minus will donate one electron pair. And form an octahedral complex. So after the formation of complex, how many unpaired electrons are left? One unpaired electron is left. So N is equal to 1. So the magnetic momentum mu is equal to root of N into N plus 2. So that is equal to root of 1 into 1 plus 2. That is equal to root 3. Root 3 is 1.7. The values they are given. 1.73 Bohr magnetons. So the first option in the column list 1 is matched with the fourth point of column 2 or list 2. But the next one, FeH2O 6 times 3 plus. Now here only one actor is changed. Fe3 plus is common, correct? Now this actor is changed. What is the name of this actor now? H2O. H2O is a weak ligand. Weak ligand cannot force the pairing. So this cannot be there. So when it cannot force, we'll try again. So now the Fe3 plus configuration. (3D5) 4s0. So weak ligand cannot force the pairing of d electrons. But 6 water molecules, when they can't force the pairing, they ask Fe3 plus, show 6 orbitals, vacant orbitals. Then Fe3 plus says, okay, I have, though my d orbital I can't pair. Now Fe3 plus has 4s0, 4p0, 4dg. Of course, 3d5 is already there. 3d5 is already there. Now the 6 water molecules, they will adjust here. sp3, 1 orbital here, 3 here, 2 here. sp3 d2 hybridization. Only outer d orbitals are involved. It is called outer orbital complex or high spin complex. FeH2O 6 times 3 plus is what example? It is called an outer orbital complex or high spin complex. The reason for high spin, 5 unpaired electrons are already present. So 5 into plus half, each unpaired electron has plus half spin. So overall spin is more. But earlier example, FeCN6 3 minus is an inner orbital complex or low spin complex. The first option is an inner orbital complex or low spin complex. Now here n value is not 1, it is 5. So mu is equal to root of 5 into 5 plus 2. Five into 5 plus 2. Root 35. Root 36 is 6. So very close to 6 value. 5.9 something. So that is there in the option 1. So B is matched with option 1. A is matched with option 4. Next, FeCN6 4 minus. So F is in plus 2 state. In plus 2 state, the configuration is 3d6 4s0. 3d6 4s0. That is the configuration of ferrous ion. Now it is approached by whom? 6 cyanide ions. So here again the actor is changing. Now they are strong ligands. So strong ligands. Force the pairing of d electrons. So how many unpaired electrons are there? 4. 4 if they are paired up become 2 pairs. So after that electronic rearrangement, because of the presence of 6 cyanide ions, the configuration becomes it becomes 3d6. So this again it becomes d2sp3. Inner orbital complex, low spin complex, diamagnetic, no unpaired electrons are there. So n is equal to 0. So one option is 0 Bm, Bohr magneton. So that is matched there. The last one, FeH2O 6 times 2 plus. So if in the place of Cn minus, if H2 are there, again the strong ligands become weak ligands. So can't force the pairing of d electrons. So d electrons remain as it is. So now the n value is equal to 4. N is equal to 4. So root of 4 into 4 plus 2, root 24, around 5. Root 25 is 5. So that is 4.90. Actually, a little bit time taking, but once you use it too, by seeing that you can find the oxidation number, you have to see the ligands, you have to see the electronic configuration, all these are first you have to calculate, then you will get different mu values. So this is a matching of magnetic momentum with a complex. The reagent R in a given sequence of chemical reactions. So they are taken first 2,4,6 tribromoaniline, tribromoaniline. It is subjected to diazotization. This process is called diazotization. So in the diazotization, the NH2 become N2Cl, N double bond, triple bond N plus Cl minus. Bromines are already there. Now finally you are getting only the ring without N2Cl. Only you are getting tribromo benzene. So this entire group is removed. It is called a reduction. This reduction is carried out either with H3PO2 or the second reagent, ethyl alcohol, or the third reagent, sodium stannite. This is out of syllabus, Na2 SNO2. This you don't require, but these two are there in the NCERT textbook. The diazonium group is replaced by either H3PO2 or ethyl alcohol. Now here, we will add some more points here. So the points are, if you take aniline, if you treat with the bromine water, You will get 2, 4, 6 tribromoanilene. You treat with HCl. It becomes NH3 plus Cl minus. It is called aniline chloride. Or aniline hydrochloride. You treat with H2SO4. You will get aniline hydrogen sulfate, because the H plus is taken by the lone pair of aniline is a base. What base it is? The Lewis base, because it's the electron pair donor. By donating the electron pair, it also accepts proton. So it is a Bronsted base also. So aniline is a Lewis base as well as Bronsted base. Due to proton accepting tendency, it is Bronsted base. It is a lone pair donating ability, Lewis base. Then after accepting the proton, it becomes NH3 plus, and the remaining is HSO4 minus. This is H plus HSO4 minus. The HSO4 minus will be there. It is called aniline hydrogen sulfate. The salt is called aniline hydrogen sulfate. Suppose if you treat with HNO3, what you will get? Same. All three are I am treating with acids only. Aniline nitrate aniline nitrate. So all these are salts. Acid base gives salt. Base is aniline. We are treating with HCl, H2SO4, HNO3. Acid base gives salt. So this has some more extra thing. It undergoes a rearrangement. Forming NH2 SO3H. It is called a sulfanilic acid. When it is further heated, the H plus is taken by the amino group. I am writing here. Then the part becomes NH3 plus, this becomes SO3 minus. on heating. The proton is taken by NH. Now this molecule finally formed contain both positive and negative charge. Ions which carry both positive and negative charges are called Zwitter ions. It is a Zwitter ion, like amino acids. Amino acids also exist in the form of Zwitter ions. That we will discuss later. NaNO2 plus HCl 0 to 5 degrees is called a diazotization. So this group is converted into N2Cl, N triple bond N, Cl minus, which is called benzene diazonium chloride. Next one I am writing acylation. Acylation. Treat with acetyl chloride. Now HCl will be removed. So NH will have so this is called acetanilide. Aniline to acetanilide. IUPAC name, acetanilide IUPAC name, N-phenyl, capital N dash phenyl, N-phenyl ethanamide. It is an amide actually. N-phenyl ethanamide. Actually, you can also do 1, 2, 3, 4, 5, 6. Now 7th I am writing. Now I am doing benzoylation. So aniline is treated with benzoyl chloride. It is called benzoyl chloride. Again HCl is eliminated. Minus HCl. NHCOC6H. It is called benzanylide. Benzanylide. Students, after going to a physiological break, they are not coming back. They are suddenly disappearing. Some are coming back, some are mysteriously hiding. So only we disappear in the air if our body fluids have same refractive index like air. If the refractive index of your body is equal to the refractive index of air, you are not visible in air. That's what H.G. Wells wrote a book, Dr. Jekyll and Mr. Hyde. Morning time is a doctor, night time is a thief. You will go, he is invisible, and you will do the bank robberies and all this. Not visible to anyone. Morning to treat patient is visible, Dr. Jekyll. Night time, Mr. Hyde. So the book title is Dr. Jekyll and Mr. Hyde. So benzanylide. Here I write a point. Acetylation can also be carried out with acetic anhydride. Acetylation using acetic anhydride. So aniline is treated with acetic anhydride. So the H plus and CH3COO, it is eliminated as CH3COOH, and the product minus CH3COOH. It becomes NHCOCH. It is called acetanilide. Now we go for alkylation, that is ninth. So when aniline is treated with an alkyl chloride, you get NHCH. N-methyl aniline. Which is a secondary amine, which again react with methyl chloride. When it again react with methyl chloride, again HCl is eliminated. So you will get N with, okay, some gap I have to find. Now this N contains 2 methyl groups. So NN dimethyl aniline. What is the name? N comma N dimethyl aniline. Nitration. Nitration of aniline. This is a very special case. You have to put an important parameter for this, very important. So actually the nitration we usually treat with concentrated HNO3 plus concentrated H2SO. Now you know the amino group is a plus M group. Any lone pair containing group connected to benzene ring is called a plus M group or plus R, positive mesomeric effect or positive resonance effect. Now these plus M groups are usually ortho-para directing. Plus M groups are ortho-para directing. So here we expect a para product I think around 50% you will get here. And very interestingly, you will get a meta product around 48%. Plus you will get ortho product around 2%. This is a very shocking observation. When amino group, NH2 group, is predominantly ortho-para directing. So whenever ortho-para products are possible, para is more possible because the two groups are away from each other. No steric repulsion. The two groups are side by side due to side by side repulsions, spatial repulsion or steric repulsion. So whenever ortho-para are possible, para is more than ortho. Take it for granted. But very interesting here, meta came in between. So immediately you ask aniline, my dear aniline, what happened to you? We are expecting only ortho and para products from you in nitration, but you are giving almost 50% meta product also. What is the problem with you? Then it says, yes, see this NH2 group can take a proton from the strong acid because you are using a mixture of two strong acids which give H plus ions. So the amino group take the H plus ion and it becomes NH3 plus. When NH2 becomes NH3 plus, it is a strong electron withdrawal. It becomes minus I. Minus I groups are meta-directing. So what is the reason for meta-nitroaniline? What is the reason for when aniline is nitrated? You should only get orthonitroaniline and paranitroaniline. But we are getting a considerable amount of meta product. The reason is the amino group is protonated and become NH3 plus, which become a strong electron withdrawing. It is called a ring deactivating group. A ring deactivating group. Ring deactivating. Ring deactivating groups are called meta-directing groups. Ring activating is called or cause ortho-para-directing because they pump electrons into the ring. It is called ring activating. So plus M groups are ring activating groups and they are ortho-para directing. Minus I groups or minus M groups are ring deactivating groups. They are meta-directing. Then how to solve this problem when you are getting a mixture of headache, when we want only a particular product? So we should not allow the amino group to accept the proton and become ring deactivating. For that, nitration is carried out in a different manner. So the next point you have to write, nitration of aniline is carried out by protecting the amino group. Nitration of aniline is carried out by number 1, protecting the amino group means NH2 group by acylation. Number 2, nitration. Number 3, deprotection. So we have to follow the same sequence. We have to follow the same sequence. So if you do the sequence, so I am going for the actual nitration. I am taking aniline. First I am doing acylation. This is called acylation. Minus HCl. This acylation is also nothing but amino group protection. I am protecting it. Then I am getting acetanilide. NHCOCH. Still lone pair is there, but this lone pair is in conjugation with the pi bond of the carbonyl group. This lone pair is not free. It is in conjugation with the pi bonds of the carbonyl group. So that's why now I am doing nitration. Concentrated HNO3 plus concentrated H2SO4. This we call nitration. Then you will get two products, orthonitro acetanilide plus orthonitro acetanilide plus paranitro acetanilide. So after nitration, you are getting only two products, ortho and para. Now you have to do deep protection of amino group. Deep protection of amino group. That is done by hydrolysis. So when you do hydrolysis, this bond breaks. H and OH. H one part, OH to the other part. Here also the bond breaks, HOH. So what you are getting? Simply orthonitro-aniline. This become NH2, NO2 plus para-nitroaniline. This is ortho-nitroaniline. This is para. They are position isomers. Para is major product. This is major. This is minor. So why it is minor? Due to steric repulsion. So nitration of aniline is not directly carried out because of 2-3 problems. One is the amino group take a proton and become NH3 plus and become ring deactivating. That is one problem. Though the ortho-para products are expected, a considerable chunk of meta product is also formed. So the question they ask you, Nitration of aniline is carried out. Option A, nitration, protection of amino group, deprotection. Number 2, deprotection, nitration, protection. They change the sequence. Number 3, protection of amino group, followed by deprotection, followed by nitration. Number 4, protection of amino group, followed by nitration, followed by deprotection. So fourth option is the correct option. So you should be very cautious. It's a very, very important point. So here we have dealt with the properties of aniline because we come across with the question. But here one more point. Aniline is less basic than methylamine. So here we are comparing the Lewis basic strength. Who will give the lone pair more easily? That is a better Lewis base. Here due to plus I effect, this is more basic. This is less basic due to LP pi conjugation. This lone pair shift this pi one shifts. Then you will get N double bond, the ring with the minus charge here. Again this bond shifts. So the lone pair on aniline is not free. It is in conjugation with the pi bond of the aromatic rings. Due to LP pi conjugation, aromatic amines are less basic than aliphatic amines. What is the statement? Aromatic amines are less basic than aliphatic amines. This is assertion, reason. The lone pair in aromatic amines is in conjugation. Both are true and R correctly explains assertion. Actually, even this is a little bit older concept. Nowadays, the modern organic texts, they are offering a different explanation also. Okay, next page we'll see. The same concept, lone pair pi conjugation, can be explained in a new manner. So benzene has sp2 carbons. Whenever carbon undergoes sp2, each carbon is left with a p orbital. Here the lone pair. These are p orbitals of benzene. They will have sidewise overlap, resulting 3 pi bonds. Not only that, these two also overlap. These two also overlap. So in benzene, all the lower lobes and upper lobes, they overlap with each other. So benzene ring has a p orbitals delocalized electron cloud above, 1 electron cloud below. When they see aniline, oh, there is one more orbital with electrons. Why can't we extend our delocalization? So this delocalization extended to the orbital containing electrons. So all become an electron cloud above, an electron cloud below. Thus this pair is not free. It is making a friendship with the entire p orbitals of the benzene ring. So from the following pairs of ions, one is not isoelectronic pair. O2 minus has 10 electrons, F minus has 10 electrons, isoelectronic. Na plus has 10, Mg2 plus has 10, isoelectronic. Mn2 plus 23 electrons, 27, 25 minus 2. Fe3 plus 26 minus 3, 23. But Fe2 plus 24 electrons, Mn2 plus will have 23 electrons. Last pair is not isoelectronic. Next is Professor Firot. Next one you write 1 point. Delta S always increases. Delta S change in entropy always increases in an irreversible process because delta S system plus delta S surroundings is greater than 0. Delta S system plus delta S surroundings is greater than 0. For isothermal process, delta T is equal to 0. delta U is equal to mCV delta T. Change in internal energy delta U, mCV delta T, where delta T is equal to G. So delta U is equal to mCV into 0. So for an isothermal irreversible process, delta S is greater than 0, delta U is equal to 0. In which of the following arrangements the given sequence is not strictly according to the properties indicated against it? HF less than HCl less than HBr less than HI, increasing acidic strength, correct, because due to decrease in bond energy. Yesterday also discussed. H2O less than H2S less than H2SC less than H3, increasing order of pKa. That is wrong. H2O is a weak acid. It should have greater pKa. So larger the Ka value, larger the Ka value, or smaller the pKa value, stronger is the acid. Since H2O is the weakest acid, it should have the highest pKa value. But they are given pKa of H2O is least. That's it is wrong. Next one, ammonia, phosphine, arsine, stibine. Increasing acidic character, correct. CO2, SiO2, SnO2, PbO2. Increasing oxidizing power, correct. So when compared to CO2 plus 4, the PbO2 plus 4, this is having more tendency to gain electrons and gets converted into Pb plus 2 state. So greater the tendency of accepting electrons, stronger is the oxidizing ability. So the bottommost elements, they want to get the lower oxidation state by easily accepting electrons. That's how we have studied this point also long ago. Why PbI4 does not exist? It readily decomposes to form PbI2 plus I2. The plus 4 state is being converted into plus 2 state. So Pb readily wants to convert the plus 4 state to plus 2 state by taking 2 electrons. The I minus will give that electrons. Here I minus is a strong reducing agent. Pb plus 4 is strong oxidizing agents. When they are together, they undergo reduction and oxidation, presenting lead diiodide. The next one, the intermediate compound X in the following chemical reaction So toluene is treated with chromyl chloride. It is a clear example of this question. Memory recall type question. CrO2 Cl. This is called chromyl chloride. So with chromyl chloride, this reaction is called Itard reaction. You will get an intermediate. The intermediate structure you have to write, it's already given. CH, OCROH, Cl2 twice. Which on hydrolysis gives benzaldehyde. So this benzaldehyde preparation by Itard reaction, actually intermediates we don't care because they are formed and immediately converted. But sometimes the examination, because in order to screen the students, they are expecting perfection, whether he knows an intermediate or not. So that's why the question is asked. In most of the exams it is asked. Suppose if benzene is treated with CO plus HCl in the presence of anhydrous aluminum chloride, then also you get benzaldehyde. This is called Gattermann-Koch formulation. Gattermann-Koch formulation. Here one more important point is that in Gattermann-Koch formulation, the attacking reagent is formyl carbocation. This is the electrophile or attacking species. Attacking species called formyl carbocation. This is also very, very important. Gattermann-Koch formulation. Okay, next is Firat. The next one is also Firat. So 2 Firats are over. So 95. Just in the 2 days or 1 day back, we discussed all the methods of preparation of alkanes. If you look at that chart, you can see decarboxylation of sodium salt of carboxylic acids. In the decarboxylation of sodium salt of carboxylic acids, we have used NaOH plus calcium oxide. See that in your notes. Here that CaO is not given. They are asking the reagent, half part of the reagent they are asking. So what is the decarboxylating agent? NaOH plus CaO, which is called a soda lime. We also had one more point. The purpose of lime is to keep the NaOH in dry state. The purpose of lime is to keep the NaOH in dry state. Okay, now you take a break. So this is how formyl carbocation, the electrophile is generated in the Gatterman-Cook formulation. But again, the matching same thing. In the list 1A, benzene COHCl anhydrous aluminum chloride, that is matched with Gatterman-Cook formulation. A is matched with 2. Next, RCOCH3. NaOX. NaOX gives halo form. It's called halo form test. I think we already discussed this part. Halo form test required methyl keto group. Compounds containing methyl keto group react with sodium hypohalite. Sodium hypohalite, or you can take chlorine in the presence of NaOH, or you can take bleaching powder in water, give halo form. And we already discussed one more point. In halo form test, the methyl group of methyl keto. Yes, anyone? In halo form test, the methyl group of methyl keto is transformed into halo form. The remaining part is converted into salt of carboxylic acid. If you forget this, you repeat this. In halo form test, the methyl group of methyl keto is converted into halo form. And the remaining part is converted into a salt of carboxylic acid. So chlorine in the presence of NaOH. This is methyl group. You can shortcut into two parts. Methyl group of methyl keto. This part is converted into halo form, chloroform. The remaining part is converted into a salt of carboxylic acid. We take 2-butanone. If it is treated with NaOCl, sodium hypochlorite. Again the methyl part, this part, two parts. So methyl part is converted into chloroform. The remaining part is converted into salt of carboxylic acid. COON, sodium propionate. Now I take C6H5, COCH, called acetophenone. I treat with I2 plus KOH. Again the methyl group of the methyl keto, this is called methyl keto. What is the required group for halo form test? Methyl keto group. Methyl CH3, CO means keto group. So again in that methyl keto group, the methyl part is converted into halo form, called ido form. The remaining part, C6H5, COOK, potassium benzoate. If it is sodium benzoate, very good food preservative. The jam you are eating or the fruit juices which are stored, packed fruit juices, the packed pickles all contain a preservative. What is the most commonly used preservative? Sodium benzoate, C6H5 COONA. This is 3-pentanone. I2 plus NaOH. No action. No ido form. But if I take 2-pentanone, I2 plus NaOH, immediately it will give ido form. Plus the remaining part COOK. So here 2-pentanone and 3-pentanone are distinguished by haloform test. This is what? 2-pentanone. This is what? Both are metamers. Alkyl groups are different, having same functional group. 2-pentanone, 3-pentanone, we don't call them as position isomers. We call them as metamers. So in which 2-pentanone having methyl keto group will give the haloform test. 3-pentanone, no methyl keto group, no haloform test. Similarly, here I wrote acetophenone, and if I write benzophenone, C6H5, CO6H5, it is called benzophenone. Chlorine NaOH, no haloform test, no chloroform. But acetophenone will give. Acetophenone and benzophenone are distinguished by haloform test. 2-pentanone, 3-pentanone are distinguished by haloform test. So actually in the haloform test, we have to give one more input here. Not only directly C double bond O groups. CH3 C double bond O is the essential group required for haloform test. But some alcohols, though they do not contain CH3CO group, on oxidation they will give that. They also undergo haloform test. For example, methyl alcohol, chlorine and NaOH give haloform. No methyl keto group. It is an alcohol, how it contains keto group. But chlorine is an oxidizing agent. It will remove 2 hydrogens. So minus 2 HCl, resulting CH3 CH double bond. The required group is formed. This will again react with chlorine, forming CCl3. CCl3, CH double bond, which is called a chloral or trichloroacetaldehyde. Now this undergoes hydrolysis. H plus OH minus, forming what? Chloroform plus HCOOH, formic acid. This formic acid reacts with NaOH, forming HCOO Na, sodium formate. So ethyl alcohol also gives haloform test. Isopropyl alcohol or 2-propanol this also on oxidation gives ketone. This will give haloform test. So among alcohols, ethyl alcohol give haloform test. 2-propanol or isopropyl alcohol gives haloform test. Here I am writing 2-butanol. Br2 plus KOH. First, this part is oxidized. It is a secondary alcohol. This is also a secondary alcohol. Secondary alcohols on oxidation give ketones. So this secondary alcohol on oxidation with the bromine gives a ketone first. So this ketone has methyl keto group. So it will undergo haloform test, forming bromoform plus remaining part CH2 COOK, potassium propionate. So haloform test is a bigger perspective. You should be very cautious to undergo haloform test. The compound, the reagents can be a sodium hypohalite NaOH, or chlorine in the presence of NaOH, or bromine in the presence of alkali, or iodine in the presence of alkali, or bleaching powder in water medium. Any of these 5 reagents, when treated with compounds directly methyl keto group or indirectly alcohols which can give that keto group, methyl keto group. So only 2 types of compounds undergo haloform test. One is the compounds which directly contain methyl keto group. The other is the alcohols which can give methyl keto group on oxidation. So these 2 class of compounds, they give haloform test. Fluorine is extremely reactive, so it will react in an unexpected way, so it cannot be controlled. So fluorine we don't do, because how it oxidates, it breaks the CC bond also. Here we are breaking the CH bonds and substituting with chlorines. It is called alpha halogenation. This carbon is called alpha carbon. So when treated with the halogen, you are getting a tri-alpha halogenation, trichloroacetal here. But if you use fluorine here, it breaks the CC bond also. So due to extreme reactivity of fluorine, we don't do fluoroform. CHF3 we don't study. We study chloroform, bromoform, iodoform. All are sweet smelling liquids, which are, especially the chloroform, sweet smelling vapors, are having the property of anesthetic property. That's why during surgery, what the anesthetist will do, he will bring a balloon containing chloroform vapors and squeeze into your mouth. They will put a funnel in your mouth, the balloon is inserted in that, you will ask 2-3 questions and squeeze it. So the entire chloroform vapors goes into lungs. Lung layer absorbs that and you will feel unconscious. A general anesthetic. They will do the surgery. Depending on your body weight, duration of the surgery, the anesthetist will decide how much haloform should be given to you. So that is anesthetic property of chloroform. Bromoform is a pale yellow, colorless liquid. Chloroform is a pale yellow, sweet smelling liquid. Chloroform is colorless, sweet smelling liquid. Iodoform is a bright yellow, sweet smelling solid. But we don't study about fluoroform, CHF3. No. How many haloforms we study? Chloroform, bromoform, iodoform. So that's why we never use fluorine. Because to handle fluorine in the laboratory, fluorine gas is not available. Even if in the research lab if it is available, you should be protective, wearing entire masks, all these, because fluorine when it touches your skin, it will react with the calcium ions of your muscles and form calcium fluoride. You will get severe burn injuries, deep burn injuries, which are difficult to heal also, because calcium is removed from your body. That is the problem with fluorine. That's why chemistry of fluorine is only done in the advanced level, research levels, not in the normal laboratory levels. Even fluorine cannot be stored in the form of fluorine in cylinders, because if any leakage occurs, most of the people will be affected. That's why fluorine is stored in the form of an interhalogen compound called chlorine trifluoride, ClF3. Direct fluorine is not stored. It is a T-shaped molecule, ClF3. 3 bond pairs, 2 lone pairs. So what is the shape of ClF3? T-shape. 3 bond pairs, 2 lone pairs. sp3 dehydrogenation. Okay. Now, okay. So B option is matched with haloform test. A option is matched with Gatton and Co. Next, alcohol and carboxylic acid. When treated, you will get a fruit smelling ester. It is called esterification reaction. C2H5. So in acidic medium, esterification, the first step is the protonation of oxygen. So whenever oxygen is protonated, it will become OH plus. No, we already repeatedly discussing the same point. O don't want to carry positive charge. It will ask the pi bond to shift. Then carbon is going to become plus. The plus charge of carbon is attacked by the lone pair of alcohol. Then you will get CH3, COH, another OH, another C2H5OH. This O become plus now. Again, this O is very unhappy because it's carrying plus. It says, my dear H plus, you give your bond to me and lose as H plus. That H plus is gained by another OH group. Then it becomes CH3, COH, this is C2H5, this become OH2 plus. Now this OH2 plus is a good leaving group, good Lg. OH is a poor leaving group, OH2 plus is a good leaving group. Many times we discussed. It leaves as water. Then the product is CH3, C, OC2H5, OH, carbon become plus. To satisfy the positive charge, the lone pair shifts, then it becomes CH3, C double bond OH plus, OC2H5. Finally, proton is lost. This is the final product, CH3COO, C2H5, ethyl acetate, ester. So minus H plus. So if you observe the entire reaction, it is protonation, deprotonation. First step, the double bond O is protonated. Second step, the C2H5OH, the H plus is deprotonated. Again loss of water, again deprotonation, again deprotonation. So this is esterification reaction. Esters are characterized by their fruit smells, their fruity odor. So whenever a carboxylic acid is given, if you are asked to identify whether it is carboxylic, for example, vinegar you know, vinegar smell you know, because most of the Chinese method of preparation of food, they add vinegar. It is a dilute acetic acid with a very pungent odor. But many carboxylic acids are given. To identify whether it is carboxylic acid or not, you have to add an alcohol in the presence of an acid, dehydrating agent. You will get a fruit smell ester. That is called esterification reaction. So that is matched with esterification, C option. Last one, D option. Hell-Vollard-Jelinski reaction. HVZ reaction. So in HVZ reaction, when acetic acid is treated with chlorine in the presence of red phosphorus catalyst. So these are alpha carbon. These are called alpha hydrogens. Presence of red phosphorus. One more H is replaced with chlorine in the form of HCl. You get a trichloro acetic acid. So this is as a whole, you can call it as alpha halogenation. Alpha halogenation. Finally, you will get a trichloroacetic acid, and this reaction was discovered by Hell-Vollard-Jelinski. Hell name is very interesting. Over. '96 is over. 97. '97. Write 2-3 points. Sodium borohydride, NaBH4. Sodium borohydride, NaBH4, can reduce both aldehyde and keto group into alcoholic group. So NaBH4 in water, the aldehyde group is reduced to alcohol group. You will get a primary alcohol. Similarly, keto group, you will get secondary alcohol. This is the first point you should know. So in this process, NaBH4 gives Na plus BH4 minus. BH4 minus again convert into BH3 plus H minus. Here actually H minus is the main hero. It will attack, it is a nucleophile. So nucleophile always attacks positive carbon. Nucleophile always attacks positive carbon. This carbon is positive. Then you will get RCH2 O minus. This again takes a proton from water. Resulting primary alcohol. So it is called hydride ion reduction. Sodium borohydride reactions are called hydride ion reductions. H minus is called hydride ion. It is a nucleophilic addition as well as hydride ion reduction. Second point, it is less reactive than lithium aluminum hydride. It is less reactive than LiAlH4. Third point, soluble in all protic solvents like alcohol, water, ammonia, soluble in all protic solvents. Next, it only do selective reduction of aldehyde group, CHO group, in the presence of, it only do selective reduction of CHO group in the presence of ester group COOR or NO2 group. So with this background, you write the given molecule. CH3, CH2, CO, OCH. This is treated with sodium borohydride in alcohol. So it is ester group, can't be reduced. Can be reduced. Selective reduction. So when keto group is selectively reduced, it gets converted into CHOH. All the remaining groups are intact. So this group is reduced. CO group is reduced to secondary alcoholic group. Suppose if it is aldehyde group, it is reduced to primary alcoholic group. So it do selective reduction. Very important point. So question number 98. Which of the following molecule is non-polar in nature? SbCl5 due to its symmetrical structure. Trigonal bipyramidal structure. Two axial bonds cancel with each other. SbCl5. These are 180 degrees. They cancel their bond moments. These are 120 degrees. They also cancel with each other. So overall mu is equal to 0. When mu is equal to 0, it is non-polar. Mu is equal to 0 for all symmetrical molecules and linear molecules. Here SbCl5 is symmetrical. Now the next question. that is environmental chemistry, presence of red phosphorus. One more H is replaced with chlorine in the form of HCl. You get a trichloro acetic acid. So this is as a whole we can call it as alpha halogenation.